Good morning. My name is Ruth Clarke, and I'm a civil engineer who's worked in the world of water and computational fluid dynamics for about 25 years. I'm going to speak today about large-scale flood modelling, how it can help us engineers understand flood risk in areas of data scarcity, but also how it can help supplement some of the high-resolution flood data that's already available. So in the next 15 minutes, I'm going to attempt to introduce Fathom, which is the company I work for, and explain what we do, why we do it, and how we do it. And I'm going to follow that up with some use cases, just to sort of demonstrate real world use of this kind of data. So I'll start with who are Fathom. Basically, Fathom is a company based in Bristol in the west of England, which was born out of the University of Bristol in 2013. It was founded by two guys who were undertaking their PhDs at the University of Bristol at the time. And the problem being solved was how to generate large-scale flood models, so that's continent or global scale, using remotely sensed data. The company now is about 40 people strong, and 3/4 of those are scientists. So the company's got many years experience working in the insurance sector, but it's becoming much more involved in the engineering side of flooding. So due to the history of the company, research is still extremely key to what we do. And I would suggest, I can't obviously go into it at the moment, but I'd suggest that if you're interested, going along to our website, there's a bibliography there showing a lot of the research that we've done. So the research is published in some of the top journals, so it's peer reviewed, and you can take a look at it there. So next, the models. What do we do and why do we do it? Well, in the last 25 years, there's been a lot of improvements to the modelling techniques included in a lot of the software solutions commonly used to build flood models. So we've seen steady state to unsteady or dynamic models being developed. We've gone from extended one-dimensional cross-sectional models to coupled 1D, 2D models. There's been lots of tools that have become available, such as genetic algorithms for parameter updating and the calibration process, all manner of different things, some of which I think we can agree are more useful than others. And one of the big drivers and things that's changed the flood modelling space, I guess, is that increasing compute power that's gone along with at the same speed as these developments. So over a relatively short period of time, more detailed, more complex models over larger areas are within reach. The downside of that is detailed models require high resolution data, so they need LiDAR data, they need cross-sectional survey data of river channels, they need surveyed embankments, they need hydrometric data, they need rainfall data. And in data scarce areas, this will all need to be collected in order to do that. And that will be expensive and will take time, even when it's just over a small area. So if you're starting to look at flood risk over large areas, you can imagine the complications involved. So why is large scale modelling important? Well, the most costly and damaging flood events generally have a regional, even continental scale footprint. So if we look last year, there was huge floods in Belgium, Germany, and the Netherlands and Switzerland. That was in July last year. And also in August 2017, I think the most costly event on record in the US, Hurricane Harvey in Texas and Louisiana. So it's not just looking at specific events, but when you want to do things like plan or look at asset resilience, large scale models can allow you to look at this over larger areas without having to do very detailed modeling. You can get a good understanding of the areas most at risk. So in order to do that, you need to have some type of framework to collate that data, to build and simulate the models. And what we do is very much based in science and produces results that are consistent across the model. So our global data is consistent globally. So using these large-scale models will allow you to identify locations which are of the highest risk of flooding across a large area. And that allows you to prioritize the building of detailed models where you have concerns about maybe your infrastructure project or looking at asset resilience. Providing this both for the current and for the future climate scenarios allows you to give a bit more resilience going forward. So what are the challenges and considerations when you're building these really huge models? So when you're moving from small to large scale, there are quite a lot of challenges. So the first one, data, is key, especially elevation data. When you're looking at huge two-dimensional models of flow across the globe, you need to understand what the elevation of the Earth is. So that's one thing, but there are many other challenges. Hydrography. Where are the rivers? Stream flow. Is there a gauge network, or will you have to look at some type of donor catchment approach? Do you have rainfall data? Do you have tide gauges? Do you have river defence information? Soil types? What about flow going into stormwater drainage networks? So it's not just about getting that data, it's also about understanding the quality of that data, what to do when data is missing. When you've got time-dependent data, how long are the records for? How can the model results be verified? So all of these considerations need to be addressed when you start to look at building these large-scale models. So building countrywide and global models required automation. You can't approach it in the same way that you would building a small flood risk assessment model. And the different approaches will be taken in different models. So for example, in the US, which is obviously a data-rich area, the location of rivers is provided by the USGS hydrography dataset. Whereas in our global model, we rely on an algorithm developed with the University of Tokyo, which can allow all stream and river locations globally to be identified. One of the other challenges when you work in this field of producing large-scale global models is the fast-moving developments in research, especially around climate change, because we're not just interested in what's happening now, we're interested about what's going to happen in the future. So needing to keep abreast of all of that information and make sure that it is built into our frameworks and into our models means that we do have to regenerate the data every so often. At the minute, it seems that there's a major update every 18 months. That might change depending on the speed of development of research, etc., going on. So what I'll do now is come on to some use cases to explain the why and the how in a little bit more context. The first use case I'm going to talk about is Think Hazard. So this is the World Bank's Global Facility for Disaster Reduction and Recovery website, and it provides a general overview of different hazards, so cyclones, earthquakes, etc. And this website should be considered in project design and implementation to promote disaster and climate resilience, basically. So Fathom have provided the inland flood information for the current climate scenario for this portal. So that's both the fluvial and the pluvial flooding, and you can go and access that and go and have a look at it by googling Think Hazard. The next use case that I'm going to come on to is the production of emergency flood bulletins. So the UK Foreign, Commonwealth and Development Office will request emergency flood bulletins for specific events to be generated, and Fathom works with a number of partners, which I've got up there on the slide, to do this. So this particular one is a tropical cyclone which hit Mozambique in January of this year, and the reports provide information relating to potential risk, exposure and impact prior to the cyclone's arrival. So we run these models in conjunction with all the other partners and produce this information, which allows people to take action, move people, evacuate them away from danger. So we need to get these done quickly and out the door so that people can actually have the best chance of not being as adversely impacted as they could be. The next example is a World Bank example. And this particular one is some work in Bangladesh. And this is basically providing current and future climate scenarios of flooding to minimise flood risk for infrastructure development. So understanding what the likely impact going forward will be if you build in certain locations. And the next slide again is a very, very similar case. This is for Fiji, and similar to the previous slide, it's looking to assess the flood risk due to climate change to maximise resilience going forward. Now, all of the case studies, the 4 case studies that I've spoken about to date have been in areas where there is data scarcity. The next 2 examples I'm going to speak about are US-based examples, and the US obviously is a data-rich country. However, even in these locations, large-scale models can be very useful. So this particular example is the Nature Conservancy, and this study is work that we undertook to look at how to explore. Well, we provided the data to the Nature Conservancy, which is a US-based environmental organisation which aims to conserve and restore natural environments, and we provided that information so they could explore floodplain connectivity and then identify structures which may be removed. So combining flood risk data with current and projected populations, land use, this all allows Nature Conservancy to understand the benefits of avoiding development in natural areas. And the final use case study I'm going to mention is the Texas Water Development Board flood quilt. Now, I'm not going to talk about that in any detail whatsoever, and the reason for that is that the Texas Water Development Board are presenting on this very topic here at ASFPM once in this session on Tuesday, session A4, that's in Tuesday morning, and once in session C4 on Tuesday afternoon. So I would encourage you to go and catch them there and find out a little bit more about it. But in essence, a very brief overview, in 2019, Texas Water Development Board became responsible for the regional and statewide flood planning. At that time, less than 40% of the state was mapped with detailed flood models. So whilst that work of building those detailed models, collecting the data, etc., was ongoing, which is obviously, as I said, quite a timely undertaking, the interim solution to supplement the existing 40% coverage of detailed models was to backfill with large-scale flood mapping data to provide this flood quilt view so that they could cover the whole state with good accuracy whilst they waited on the very detailed models to be created. So that finishes what I was going to talk about. I hope it's given you some food for thought on the topic of large-scale flood mapping. I'd welcome any questions either now or any other time throughout the conference, or indeed via email after the event. We are at booth 802, so there's both myself and my colleagues Gavin and Holly, so please do drop by for a chat. I thank you very much for your attention and hope that you have a great conference.